Hello everyone. Today we're going to talk about tSNE, or T-distribution stochastic neighbor embedding. tSNE is not only one of the most popular methods for visualizing high-dimensional data, but it was also one of the first methods that ever came out where the dimensionality reduction was designed primarily for visualization. So tSNE also operates under the premise of most dimensionality reduction methods that we have a high-dimensional ambient space from where the data comes from. And so your measurement dimensions can be very large. But what tSNE is trying to do is it's trying to find a low dimensional space that preserves certain structure in the high dimensional space. But it doesn't focus on variance or manifold distances, but rather on neighbors. So if we have a point I, tSNE tries to preserve its neighbors. For example, this point J is a neighbor of point I. So it tries to find a low-dimensional embedding where J is also I's neighbor. The way it basically operates is actually to compute a Markov normalized affinity in the high-dimensional space and the low-dimensional space. And it greedily moves points in the low-dimensional space. So for any point I, the neighbor probabilities that are found in the corresponding row of the Markov normalized affinity matrices match as closely as possible. And so you have to repeat this greedy movement because it moves in small steps towards arrangements of points that increase the match between the high-dimensional neighborhood probabilities and the low-dimensional neighborhood probabilities. So you might notice that it doesn't involve any eigen decomposition or anything like that. It is not a variant of a kernel PCA method. So just to go back a little bit, in order to compute tSNE, you would usually need to go from distances, for example, a Euclidean distance, to affinities. First I'm going to just explain SNE, or stochastic neighbor embedding, which usually uses a Gaussian kernel, like we did in diffusion maps to compute affinities. And not only does it use a Gaussian kernel, but it also uses this row normalization that makes each row sum to 1, and therefore each row be a probability distribution. So we have this Markov matrix that represents basically random walk probabilities as in a diffusion map, but I will warn you that tSNE does not actually use a random walk. This matrix is not powered. tSNE does have one other feature, though, is that the kernel is always adaptive bandwidth. This means that the standard deviation of this Gaussian is adapted so that roughly each point has the same number of effective neighbors, or the entropy of the neighborhood of each point is even. And so the effect of this is that you get even density plots in tSNE. The actual optimization of tSNE tries to match high-dimensional neighbor probabilities with low-dimensional neighbor probabilities using a divergence that's called Kullback-Leibler, or KL divergence. So now divergences are a little bit like distances, but they're not quite distances. They are asymmetric. Kullback-Leibler divergence actually comes from the field of information theory, and it measures the amount of information gained or extra information available when updating one distribution to another. And we're going to cover this later when we cover more information theoretic quantities. But for now, you can see that this is a way of matching distributions, and that if you had a very close relationship between these probabilities, you'd get the log of 1, which is 0. And so this penalty would be very low. Here's an example of Kullback-Leibler divergence on a continuous function. So you have two Gaussian distributions, P of x and Q of x, and at each point you have this ratio, log of P over Q. And then you're going to weight it by P or Q, by P here. And then you end up having this area, and divergence is actually the area under this curve. In tSNE, what's actually used is a symmetrized cost divergence. So because we have an asymmetric matrix, tSNE uses P of I comma j plus P of j comma I over 2 to compute divergence. And once this divergence measure is computed, you move each point based on stochastic gradient descent. So you take the derivative of the point with respect to this quantity, and you move in the direction that reduces this penalty the most. So in a nutshell, the steps of tSNE are to compute high-dimensional neighbor probabilities and then low-dimensional neighbor probabilities. You see here that the low-dimensional neighbor probabilities have a sigma or bandwidth of 1, and the high-dimensional neighbors have an adaptive bandwidth, usually, specific to each point I, and we have a Kale divergence cost function, and we have the derivative with respect to the low-dimensional embedding location of each point I. You have iterative updates that move in that direction with a certain learning rate or step size, and this process is repeated until convergence. So what does this actually look like? So I'm not going to show this to you on a Swiss roll. Might not be very good because it's not preserving certain kinds of manifold distances, but what SNE type embeddings are good at preserving is cluster structure. So here we have a really famous data set for machine learning. It's these handwritten digits that are called MNIST digits. And these are often used as a benchmark in machine learning for classification or clustering methods. So the idea is that we have these different digits that we as humans can recognize, but they're all written a little bit differently from each other, and they are actually a high-dimensional input because these are 28 by 28 pixel images. And if you have an embedding that groups all the zeros together, all the ones together, all the twos together, etc., you must have an embedding that preserves this kind of grouping structure. And you see here that this is SNE. It does preserve grouping structure, but things are pretty crowded. You see like overlaps between groups, so things aren't really being pushed apart as well as you might want to really clarify the grouping structure. One of the reasons for that is a problem that exists with a tSNE penalty. This is not the only result of the problem, but this is one of the results of the problem. Take a look here at the Kale divergence penalty. I mentioned that it's asymmetric. In particular, you multiply by the high-dimensional neighbor probabilities. This whole penalty is scaled by that. So what that means is, if 2 points are neighbors in the original data, then this quantity is high, and whatever this is scaled up. So that means that there is a large penalty if you take neighbors in the high-dimensional space and you move them apart in the low-dimensional embedding. But look at the reverse. If 2 points are not neighbors in the high-dimensional space, then this is effectively 0. And so there is no penalty for any value of this. That means it doesn't even matter what this is. If this is low, who cares? That means that tSNE does not carefully control what it does to things that are far apart in the original data space. So one way to work with this and still push things apart is to actually use a heavier tailed distribution that doesn't drop to 0 quite as fast as a Gaussian distribution. So, and then this might help that our MNIST classes weren't as pushed apart as we would want them to be. And so to do this in tSNE, the authors moved to a student t distribution, which does indeed have a heavier tail than the Gaussian distribution. When you run tSNE on MNIST, you do get much better separation of the digits. And this is one of the reasons why tSNE is very popular, because often users of tSNE are working with biological data where they want to see clusters. They also want to see how many data points are in clusters. And because of the even way that tSNE spreads points out, the size of the cluster reveals to you how many points are in the cluster. So just to compare to diffusion maps and FATE a little bit, we used a Markov random operator, but we did not use diffusion or walking, did not use eigendecomposition. We did not use any form of MDS or distance preservation. But we did try to match near neighbors using Kernel divergence. And of course, that is the main quantity that is preserved in tSNE.